So let's rejoin to this section 6 of this conference. I would like to start thanking all the participants for coming. It's a great pleasure for us having you here. And without further ado, I would invite Professor Turing from Universidad Chile, Católica Chile, to start his presentation.
Thank you. Thank you so much for being here in the last session of the day. So I'm going to present to you this paper is called Lumpy Forecast. This is joint work with Isaac Vallee. And let me start with the motivation of the paper. Actually, we're in the central bank, and I need to motivate why expectations are relevant or important for macro, for decisions from both the central bank position, also in the price set of decisions. And typically, so this paper is going to be about the recent exponential use of survey data to try to learn things about how agents form expectations, how fast do they learn, and typically through theories of expectation, through this survey information, we typically test whether the forecasts are rational, whether they are behaving in a strategical way, etc. So the underlying assumption for this, for using this type of information is that, well, when you ask agents to tell you a prediction for inflation, GDP, whatever, what they disclose, what they put in an Excel spreadsheet, if you want, in a survey, is actually a true reflection of what they believe, what they truly expect is going to happen, okay? So this is the underlying assumption. I'm going to try to challenge this assumption, saying that sometimes their belief may not be reflected by their forecast, okay? So this is the motivation for the paper. We ask if does this assumption hold for inflation surveys, and if not, what drives this difference? This will obviously have some very important implications for the conduction of monetary policy if there is really a mismatch between the beliefs and the forecast. Okay, so I'm going to present to you some new facts using a survey of professional forecasters in the US that are going to predict the end of year inflation. So think about the inflation towards the end of the year, towards December. And I'm going to show you 3 facts. The first one is that there's evidence about lumpiness. There are episodes of inaction, so forecasts are going to remain strictly constant throughout the time. Those episodes of inaction are really followed by large revisions in the predictions. The second thing is that the frequency of the revisions is not constant over the horizon. It's going to change throughout the horizon. In fact, that frequency is going to fall with the horizon along with the size of the revisions, so the extensive and the intensive margin. And third, there's evidence about strategic behavior. So the distance to the consensus, the distance to what everybody else is saying really matters in terms of understanding what is going to be a trigger in terms of revisions. Through this information, we're going to present a new model that is going to combine 3 ingredients. The first one is we're going to allow for the agents to learn in a Bayesian way. On top of this, we'll have some fixed revision costs to produce some inaction, to produce some inertia in terms of the revision process. And also, we're going to allow for strategic concerns from the forecasters itself. We're going to present what is called an SS-type model, but for forecasts, not for beliefs. Then we're going to structurally estimate the model and going to then quantify the role of each of these 3 frictions to reproduce the data that we observe in the survey. I'm going to, so in the paper we have 3 applications. The first one is going to say something about how heterogeneous are forecasts in these big surveys. I don't think I have enough time to show you this today. We're going to focus on the second application, which is there's a lot of discussion in the literature about deviations from rationality. You typically conduct this usual rationality test. I'm going to show you how what the model can say about this rationality test through the lens of the inaction. And then we also have some implications for changing the fundamental volatility that obviously I'm going to have time to show you today. So I'm going to just focus on the second application, okay? I'm going to skip the literature for sake of time. Let me just say you a couple of things about the data. So as I mentioned at the beginning, there's going to be inflation in the US. We're going to use Bloomberg, ECFC survey professional forecast. The evidence that we have is at the weekly level. We're going to aggregate this at the monthly level. We're going to focus on a fixed event forecasting scheme, which is basically agents are going to predict last year, so the end of the year inflation, so the inflation that you will serve, let's say, in December. But one of the key things about this survey is that you can observe the consensus, so you can observe what everybody else is saying in real time. So you just go through the Bloomberg platform. I'm going to show you a snapshot from the platform, and you can see what everybody else is saying. So you don't have to wait for the typical survey that you observe what everybody else is saying with a month of delay. You can actually say it in real time. We do have some roughly 100 forecasts for 14 years. I'm going to split the sample between what we label is going to be like normal years, and we also have an exercise for turbulent years, so uncertain years, which is basically the Great Recession and the COVID pandemic. And we can classify the forecast in 4 different groups. I'm not going to have time to show you how different they are today, but we can also do this. And one of the nice things about this survey is that now there's recent evidence that the inflation expectation actually drives the trading behavior of the forecast, in the sense that they truly use this information to actually trade in the stock market, okay? So they are really using this information. So not just a game for them, okay? So this is like you set your minds in the fixed event scheme. Think about the end of year inflation. This is object that we have here, which is basically like a weighted sum from the inflation between January and December. That's nothing else. And you will start producing a prediction. Let's say that you are in January. You want to predict what is going to happen to the inflation towards the end of the year. And I'm going to keep track on your predictions as the horizon starts shrinking, in the sense that, well, I'm going to ask you for your predictions then in February, then in March, and so forth, okay? The nice thing about this is that I know that between January and February, a relevant piece of information appears, which is the monthly realization of inflation. If you collect those 12 realizations, you will get the actual object that you're trying to predict, okay? This is perhaps many of you are familiar with Bloomberg. This is just to flash you that, well, you can see if you go to the platform, you will see what everybody else is saying in real time. You can see it at any time. Also, you can see what all the participants are saying in real time as well. For in this case, it's inflation, but you get information about GDP and employment, so forth. So this is an example of lumpiness in a particular year. So this is the year 2019. Think about these 3 forecasters here. As I said, there's roughly 100 of them, but this is just to make the point. And in this year, look at this horizontal line here is the actual value of inflation towards the end of the year. So you can see that, let's say, 12 months before the release, so this is January, lots of dispersion in terms of their predictions. Then they start acquiring information, and then obviously they start converging to the actual truth. But 2 things I like to flash here. The first is that, well, you see from this red line, which is standard Chartered, they stop revising at the 7th horizon. So there's no more revisions after that. Although you got information which can be relevant for you, and although you know towards here that perhaps your prediction is not going to be exactly what the actual inflation is going to be, you choose to keep that prediction there. This is the sense of the lumpiness, the sense of the stickiness, if you want, in terms of the predictions. Another example is this black guy here, which is the Wells Fargo. They were actually predicting inflation very well. Then, for some reason, they interpret this signal as something that they revised downwards here, and then they revise again back. So you see a small revision here towards the truth, and then lots of revision at the beginning, okay? And then the other one, the blue one, is actually hitting the inflation pretty well, although on top of this, with evidence of lumpiness, okay? So let me show you how this looks when you average everybody in the survey, and you average across years as well. Okay, so here on the left, you got the frequency of revision, so the probability of revising a forecast. You can see that lots of revision at the beginning. Nobody's actually revising at the very beginning. There's not one. The probability is far from 1. But then as the horizon starts shrinking, you get less and less revisions towards the end of the year. This is the extensive margin. The intensive margin looks pretty similar in the sense that conditioning on adjustment, the magnitude of the revision also starts going down as you approach to the realization of the value of the variable. They are pretty accurate, so they learn. So if here in the left you see the forecast error, so deviation of my forecast with respect to the true inflation, see that they start really off, and then they start learning, they start acquiring information, and then towards the end of the horizon, they do a pretty good job in terms of the prediction. And also, if you look at the hazard rate, which is basically the probability of revising conditioning on the age of a forecast. Okay, so a forecast of age 1 is a forecast that's been kept fixed for just 1 month. And this is the typical result that you observe also in the pricing literature, in the sense that the hazard rate is downward sloping, in the sense that, well, you are more lean to revise forecasts that has like age like 1, 2, 3, 4, rather than forecasts that have been fixed for 8 or 10 months, okay? And we're going to argue that the model, if the model is able to replicate this pattern in the data as well. The consensus really matters. So the idea here is we're going to run this regression about, well, the dependent variable is going to be the probability of adjustment. Here in the left is the probability of doing a positive adjustment. Here on the right, the probability of doing a negative adjustment. And you can see that the distance from the consensus actually triggers revisions. So take this example here. So if you are below the consensus, so let's say that the consensus is 3%, you are 2%, the farther you are from the consensus actually triggers revisions, in this case positive. So what this means is that you want to close the gap between what you are saying and what everybody else is saying, okay? So there's evidence about strategic behavior also in this type of service, which has been documented by the literature before as well. Okay, so let me just show you very briefly the model. So the model will have three ingredients. We're going to assume that for each of the horizons, remember there are 12 horizons here, the forecasters want to choose a prediction, which they want to label f of IH, in order to minimize the distance between with respect to the truth, let's say the true inflation. So we had preference for accuracy. You also don't want to be far from the consensus. This is weighted by R. R measures how much you care about being close to the consensus relative to the accuracy. And also there's going to be like a fixed revision cost I'm going to label kappa, which you can think about stability cost. I want to revise, I want to be accurate, but I don't want to be changing my prediction all the time. So every time I change it, I face some, let's say, reputational cost or stability preference, if you want. These are going to label as kappa. I want to calibrate that parameter. And I need to put some structure in order to how to form beliefs. As I told you, end-of-year inflation is just the sum, the collection of the 12-month realizations. The consensus is just the average of all the participants. And we're going to assume, just for simplicity, that the monthly inflation follows an Layer-1 process. And you can observe the true realization of inflation with what period delay. So this is the statistical officer telling me that last month inflation, was something like 0.4%, something like this, okay? On top of this, agents learn through a private signal, which has the truth inside, but you see it with some noise. The idea is that through the combination of these two things in a Bayesian way, you can get clearer signal about which is today inflation, the monthly inflation today. And also we are going to allow for simplicity an Layer-1 structure for the law of movement for the consensus forecast. In the information set, you observe all the past realizations of the variables without noise. On top, you observe your private signal on the current month, okay? So it's a model for beliefs. So you can prove that there's going to be a belief about inflation given by your signals. So that signals that you have will form a belief. Also, you have beliefs about the consensus, and then the nice thing about this is that you still have some unforecastable part. If you like time series and you do forecasting, you know there is some part that you cannot predict, and that part is actually depending on the horizon. It's harder to predict the value if you're in January rather than if you are in December or November. Okay, so this is how you form beliefs. Then you're going to combine your signal through the past information, and you're going to form a new belief, let's say this X hat, for the monthly inflation, and then you're going to take that and going to project that towards the end of the year. So this is the first bit here. So if you're in June, you need to project all the remaining months of the year, but also in June, you already know the actual realizations from January to June, so you just sum it there without any noise, right? So it's a combination of the past information and the projection, which has this nasty form because of the 12-month sum. Same with the consensus. The consensus, you just can project it through very simple through the Layer-1 process. And again, since the uncertainty changes through the horizon, the problem of choosing whether to revise or not is going to be horizon dependent. This is one of the main, for me, one of the main contributions of the paper. That actually can, so the stopping time problem actually changes with respect to the horizon because the uncertainty is changing throughout the horizon, okay? This is just to show you the three state variables. So you enter each period with your previous prediction about your forecast. Then you learn the past realizations of inflation and the past realization of the consensus. You observe your signal. You form a new belief about this month inflation rate. You combine it with your new belief about the consensus, and these three objects are your state. And with your state, you choose whether to revise your forecast or not. Okay, you can see it here in in the value functions, okay? So basically, you're just going to compare between the value of action and inaction. If you choose action, you choose to revise, then you have to pay this adjustment cost kappa, okay? And then, as I was saying, so it's an optimal stopping time problem with the feature that is horizon dependent because of the shrinkage of the horizon, of the term structure, okay? So this will form an inaction region that is a function of h. And the inaction region basically tells you is that you choose to revise or not, depending on your forecast being inside or outside the inaction region that it was, as I mentioned, start moving throughout the horizon. So that object is also time varying, okay? I'm running out of time. Let me show you the calibration. So there are 3 parameters here in the model. We choose these 3 models in order to pin down the 3 parameters. You can see that the model does a pretty good job. Also, we feed the model with some parameters that we estimate directly from the data. Through the calibration, you see that there is preference for stability. So the kappa is actually, is positive. So you care about this preference for not changing the forecast much. And also this preference for complementarity in the sense that the R is something like 0.4, which means that you actually care about where everybody else is. Okay, so let me skip this. So this is like the model version of the figure that I showed you at the beginning. So remember, there's 100 of them. So this is just to take 3 random years. This is the truth, and this is how they start very far from the truth. They start learning in a lumpy way, and you can see that as more information starts becoming available, they start converging towards the truth. But the rate that they learn through the lumpiness is not monotonic. That's the whole point of this, right? You can do it for different years. You can get roughly the same thing. And here's how the prediction of the model for the same figures that I showed you at the beginning, but it's completely on target. So the only thing I'm going to target is the unconditional probability of revision, which is these 2 horizontal lines there. I'm forcing the model to replicate these 2 horizontal lines, but then the behavior of the updating behavior, the extensive margin, and also the behavior of the intensive margin is completely up to the model, and you can see that the model is doing a pretty good job in terms to replicate that, on top of the hazard rate. Remember that this is very hard even for the pricing leader to do it. We also, through the lens of the model, we can replicate this as well. The model also is not very quite there in terms of the accuracy, but it also reflects the decreasing patterns of the forecast error, as we expect, on top of some additional moment. And same for the gap to the consensus. This is the data against the model. Remember that the distance from the consensus actually is going to trigger revisions. The model is able to predict that, especially in the right-hand side and the left-hand side part here. And 3 minutes. Let me just show you this. So this is like, for me, one of the main contributions that we can do through the model. If you're familiar with this expectation formation literature, everybody's running this type of regression, which is basically you need to run the forecast error as a dependent variable, as a function of a constant, as a function of the forecast revision. This is a proxy for the information set, so how you revise your forecast between 2 consecutive horizons. And then, so this is up to here is the typical rationality test that people are running. But then you can extend this rationality test saying that, well, you have preference for consensus. You can add this extra term here and trying to see if there's a correlation between the forecast error and the revision. So I care about the coefficients 0, 1, and 2 in this case. So the leaders have been using this to say, well, if people are truly rational and form expectations through full information, you should expect that gamma 1, gamma 2, and gamma 0, gamma 0, 2, and 1 and 2 should be 0, meaning that the forecast error is completely unpredictable. It's just white noise, right? There are massive deviations of rationality when you take this into the data. There is evidence about under and overreaction to private information. So people show that gamma 1 is actually different from 0, it's positive. Gamma 2 it should be, gamma 0 could be either positive or negative depending if you under or overreact. Same with the public information. And what we're going to do is going to run the same test through the lens of our model, which is what you observe here. In the data, you got so data is the red line. We get exactly the same as the literature is getting. So overreaction to the private information, underreaction to public info. And then when we introduce the lumpiness, and this is again completely on target, we're able to reconcile while you typically observe deviations from rationality, because people are behaving in a lumpy way and people are actually looking at the consensus rather than telling you what they really believe about the inflation. If you shut down, again through the model, if you shut down the lumpiness and you shut down the strategic concerns, you can actually recover what the typical rationality test will tell you about gamma 0, gamma 1, and gamma 2 being actual zeros. You can see there's the green line. But you observe this in the data, but in the data is actually lumpiness, and we claim that one of the reasons why you observe this pervasive deviation from rationality is actually because people are behaving in a lumpy way, and people are actually caring about the consensus rather than just telling you what they believe about the inflation. Okay, so I got more applications. Let me just conclude. Hopefully I convinced you that forecasts are lumpy. We extend an SS model with Bayesian learning, fixed revision cost, and strategic concerns. We have 3 applications. I'm going to refer to the paper if you're interested in any of the other 2. And in a companion project, we're actually thinking about how is the role of the lumpiness combined with the transmission of monetary policy shocks in terms to address some issues about learning and how frequent or what the speed of learning in terms of the agents. Okay, that's my time, sorry.
Thanks a lot. I'd like to invite Professor Isler to comment on his paper.
So I'd like to thank the organizers for inviting me for the conference and commenting this paper. So first of all, I should say I like the paper very much. I think it's an important, discusses important issues. And to go back, just think that one of the important issues about this is that for us to get a positive sloped supply curve, we actually need some type of slug lineage. So on the core of that, there's a more important issue. Just to remind everybody, the idea, what is the lumpiness? Lumpiness is that professional forecasters adjust inflation infrequently and revised by a large amount. And what they also observe from the data is that across horizons of forecasting, as the forecasting horizon shrinks, the frequency of revision, the variance, and the forecast errors decrease. And they also assess the role of the consensus and private information in shaping forecast revisions. They claim that the Bayesian model of belief formation with fixed revision cost can explain what they see in the data, what we see in the data, okay? So, but one key issue is that the paper actually challenges the view that the forecasts that we observe in surveys, and we use surveys a lot, accurately reflect beliefs, okay? So there is a huge literature on surveys, and that's a big challenge. They claim that essentially forecasts are a noise-ridden version of beliefs. So from what I understand, the paper is related to a previous work of Javier with co-authors, but they extend the setup quite a lot. And it would be nice to have that explicitly on the introduction. I think that's the value added from that is critical. If you look at all the setup that Javier showed to us here, it's really sound complicated. And it is, but it's solvable. There are assumptions. And once they do, they get nice results that I should have also another figure that's even better than this one, that shows how well the model reproduces final results using calibration. So, so first of all, let me address the key question of the paper, which is, do forecasts actually reflect beliefs? And the answer is no. And to give you some support on that, let me also bring here a paper with Raffaella Giacomini and Wagner, Gaglianoni, and Vasiliki, who are also co-authors of Javier. They have a simple rational inattention model that shows that there is, using the focus survey of the Brazilian Central Bank, that shows that incentives play a key role in explaining behavior of people posting forecasts, okay? So in that paper, we kind of interviewed a few people that are top forecasters for the Brazilian Central Bank. Some of them were our students. And they said something that was very interesting from the start. They said, okay, I update my model every day because we have trading to do, we have reports to write and all that, but I only update once in the focus survey because there is an incentive to do that on a given day, which is called a critical date. And of course, that's the reason why the central bank put in the incentive, because they realized there were lumpiness. So to answer the question of Javier, yes, of course, there is lumpiness, and lumpiness has to do with that. From a rational inattention perspective, you can immediately see the reason why people don't post their daily forecasts all the time in the database. It's costly, essentially, is the cost of doing this. So I think that's an important thing that the paper captures that should be there. Another thing that I think is relevant is to mention that in a survey, everyone is forecasting the same variable, right? Not only that, they're using essentially the same database to forecast that. So it's natural that you have a common factor for the forecasts. That's even intuitive, but you can show that analytically. So one issue that's important is that if you don't take this into account, then there is a problem, because in another paper with Wagner Gaglianoni, we show that tests of rationality, they need to use instrumental variables. You can't run the regressions using OLS. And then if you do use OLS, then that is inconsistent in the estimates. And that comes about exactly because of the presence of the common factor. So every forecast is a function of the same thing. So at the end of the day, the error of the test is correlated with the regressors. So that's one important issue that I think should be taken into account. Another important thing I think that I would like to see here is that a lot of people use these panels of expectations for forecasting, okay? But there is a lot, and they balance the database, the panel. Nothing wrong with that. But from a forecasting perspective, it would be nice to use the information of the people updating their information to try to forecast what the others, the missing values are. And that can be accomplished. So if you're thinking about, so that's essentially solving the ragged edge problem in forecasting, like the nowcasting literature does. So that's one thing that I think maybe should be taken into account if we want to use that for forecasting. And I think that's a noble use of the database. I think I'm going to stop here, but I like very much the paper, so congratulations.
Oh, please, Professor Turing, short replies for the comments.
Thanks, Joao, for the comments. Yes, with respect to the first one, I'm really aware of that paper because remember there was the array for that paper myself, so I really remember. As I was hearing you, it's true that you do interview the forecasters and they actually claim this, and we are silent about this, more like kind of a direct evidence about the lumpiness that we can cite, that's for sure. What else? About the second comment, yeah, this is true. There's also a lot of information in the consensus. They're actually learning from the same thing, so the consensus is actually a reflection of the public information. In the model, we prevent agents doing that because of the timing. That's why we allow them to observe the consensus with a delay. That prevents them from learning from the consensus, and then the minute that you observe the true consensus one period later, then you actually also observe the actual realization of the inflation. So there's no point for you, it's irrational for you to learn from the consensus, but this is a shortcoming given the timing. But I agree with you that perhaps we can be more explicit about this, because there's a lot of evidence, as you were mentioned, about, well, the consensus also carries information about the public release. Everybody's tracking the same thing, right? And related to the last comment, so yeah, so that I agree that that would be nice to have this kind of optimal inflation forecast for individual models. We do balance the panel, mostly to track the same guy throughout the horizon. Although it's true that some new participants starts appearing when 6 months before the release, and then probably there's some important information there that we can use for getting the point more clearly. So yeah, thanks.
Yeah, one of the issues that, sorry to say now, but one of the difference between the Brazilian Central Bank forecast and the Bloomberg is that in the Bloomberg, as you mentioned, you see the consensus
right. Yeah.
In real time.
Yeah.
And that's not the case in the Brazilian Central Bank.
Exactly, which is our point why
So perhaps that explains the interaction, the closer interactions there.
Yeah, that's a good point, thanks. Yeah. Cool.
A lot. We still have some time for the audience to ask some questions.
You showed the graph. We can see that the size of the forecasting error declines with proximity to the event. Does it decline more than expected due to the amount of months that remain in the sample? For example, if you're always looking at the calendar year forecast and it's remaining 3 months, if you analyze the size of the error, are they smaller than when you're looking at 9 months or 12? I'm not sure if what you showed is in this comparable manner. I think it would be interesting to know if it's declining simply because you're looking at 3 months of the 12-month period, or if the real accuracy increases as the horizon shortens.
Hi. I was wondering if you thought about testing your model in other variables besides inflation. And this might be informative if there are differences in costs of doing the forecast, since the cost is the main driver of lumpiness in your model. If you can argue for differences in costs, it will be informative for the mechanism you are proposing.
Questions?
All right, let me start with the second one. Yeah, we can test in other variables. Two reactions there. We focus more on inflation because of the measurement error. So typically you start looking at GDP. Sometimes I cannot tell apart if they're revising because there's measurement errors in the measure of the GDP rather than they're revising because of the actual incentives that they are showing you in the paper. So that's why we focus more on inflation, which is, I would say, a variable that is measured without that noise. But it's true that perhaps if we look at, let's say, unemployment or GDP, the cost that we estimated could change between some different incentives to get inflation right rather than GDP right. So that's a good point. We haven't really done this. And the first one, so actually I don't have a prior about how fast do agents should learn in terms of how quickly they're starting achieving the zero in terms of the forecast error. What I like about this is that you can see that the slope of the forecast error is not really constant. We can tell you something about the speed of learning. So they actually learn a lot at the beginning, but then they stop revising towards the end. And this is our story about whether they keep on learning or they just want to keep the forecast fixed. Ex ante, we thought that slope should remain constant, which I think is what you have in mind as well. But then the data doesn't tell you so. And this is for me one of the nice things about the project, because you can claim something about how fast agents learn. Because remember that inflation is persistent, so perhaps by learning a lot at the beginning, you can then serve the persistence of the value to produce something, and this is something that we are kind of disciplined through the lens of the model.
Thanks again. Without further ado, please, Professor Isler.
Okay, so predicting US recessions in real time using a big data approach. So big data. Well, first of all, this is work with, joint work with Wagner from the Central Bank and Osmani also, and Artur, who is from FGV, and Farshid, who is from Monash. And the usual disclaimer applies. So as you can see, 20 minutes is not enough to just show the whole model that you use, so I'm going to say it up front. With big data means that you have much more variables than time series observations. So think about OLS, for example. You can't invert x prime x inverse x prime y. You can compute that, okay? Because it's infeasible. The second moment matrix is not invertible. So you need some type of dimension reduction technique, okay? The way we accomplish that is by using principal components. That's the first bit. The second bit is that, but to do principal components, you need to balance the panel, because some series, they are released prior to others, and there are some holes in the database. So that's the ragged edge problem that I mentioned before. So we first solve the ragged edge problem, get the balanced database, a balanced panel. Then we use principal components to extract the common parts and implement the reduction dimensionality. After that, we use canonical correlations. With the canonical correlations, we can separate what's noise from what's cycle. And of course, we're trying to predict recession, so it's very important to get the cyclical part and throw out noise. So canonical correlation is going to serve as a device to do that. And to compute the probability of a recession, we use a probit model. And it turns out that the probit model will be a structural model in the sense that regressors are correlated with errors, so we need instruments. But the canonical correlation bit is going to offer that. And at the end of the day, so we compute probabilities, but we need to decide, is this month a recession or not? And that's where the ROC part, the ROC curve part, gets into the methodology. It's going to give you a decision decision mechanism to say this is a recession and that's not. If you get 0.7 as a probability, for example, is this a recession or not? What answers this question is exactly the ROC curve. So we're going to get to that. Of course, we all know that that's very important to predict recessions, but I think we all know Jim Hamilton who wrote that huge book on time series, and he says, if people could predict recessions, they probably would not happen. So so if Jim says that to you, what do? You try. That's what we did. So, but of course, a challenging thing. There are some added complications. First of all is the ragged edge problem that we have to solve, but the literature has solved that, so we just borrowed from that. There are things we cannot do. For example, we don't deal with data revisions, but that's a minor problem because the data set we're going to use usually has very little or no revision. And another thing we have to be careful about is not to use future information to forecast the future. That's really illegal in the forecasting. So we're going to use a bit of future information. I'll show you. Okay. So the framework has 2 bits. It's based on 2 papers. We have an old paper. Me and Vahid have an old paper that came out in Journal of Econometrics that we actually had that probit model that I mentioned before and all the canonical correlation bit that I also mentioned. Didn't have the big data part, okay? So that's the first part, but we're also going to use the ideas behind Stock and Watson's 2014 paper that they propose an approach, a big data approach for predicting recessions or identifying recessions. You're going to see in a bit. So what's canonical correlation? I guess most people don't learn or don't know that. Canonical correlation is a generalization of linear regression. Very simple. Linear regression runs a regression of one variable on a bunch of regressors, right? It minimizes the sum of squares. Now, canonical correlation, instead of having just one variable, it has a lot of them on the left-hand side, okay? So essentially, you get linear combinations. You have here coincident series that have the same cyclical pattern of the US business cycle, and you have predictive series or leading series. These are the Zs, and the Zs are lagged, as you can see. So what canonical correlations do gets linear combinations of the X's, which are the cyclical parts, and linear combinations of the Z, and gets the weights on the linear combination to maximize correlation. Okay, that's the correlation part, and these are identified sequentially from the top one to the lowest one, and you can also test whether or not the lower ones are 0. So that separates the noise from the cycle, okay? So that was in our previous paper. Now that's the probit part. As you can see, we have an identifying assumption. Y star, every probit model has a latent variable that you don't observe. What you do observe is whether a dummy variable, if something happened with the Y star, okay? And our identifying assumptions is that the cyclical bits have a common cycle with the Y star. So the Y star is going to be molded by the parts of the canonical correlation bit, okay? So it's a common cycle between that and these cycles. And it turns out that the NBER decisions, that gives you the ones and zeros that we're going to use at the left-hand side variables in the regression, they use future information. So at the end of the day, the probit model is going to have zero correlation because of that. And because here you also have the conditional expectation of the C's, but the regressors here are C's, then the error term is going to be correlated with the regressors. And you need to use instruments, but canonical correlation gives you the optimal instrument, which is the Zs, the linear combination of the Zs that's mostly correlated with the Cs. Okay? So you have a full structural model if you wish, and you can get a coincident indicator if you want, and a leading indicator if you want, using the X and the Zs. Okay? So in action, in our previous paper, we have 4 series: industrial production, sales, income, and employment. But the last canonical correlation is statistically 0. This is the p-value. So we only have 3 basis cycles that are really cyclical. And the last bit here is just noise. So we throw that out. So in our probit regression, we run the zeros and ones on the first 3 cycles, which are the significant ones. And we throw the 4th away. Okay? Fine. So canonical principal components is just there to reduce the dimensionality. Like I said, we cannot invert the matrices needed to compute canonical correlations because we have much more variables than time series observations. It's infeasible. Sorry. This is the database. This is the heat map of the database of Stock and Watson. So I have more than 250 series that are coincident. The white part here is there are holes because of missing data. And at the end of the day, we didn't use and these are, there are only 4 categories here, again. Industrial production, sales, income, and employment. But sales variables are the ones here on the bottom. They are not very informative, so we decided just use industrial production, employment, and income. Okay. Ragged edge problem, well, that's well known. We're going to use the EM algorithm. That's essentially generalized least squares. Okay. And so a summary of the methodology here. The coincidence series are going to be 178 because we don't use the sales data. The leading series are about 300. But if you add legs of the leading series to forecast the coincident part, and you also add legs of the coincident as well, leading and coincident, you can easily get to 1,000 series. So much more than the 636 observations that we have in time. So we really have a big data problem here, okay? So just to get an idea, we're going to generate vintages for every month of the forecasting bit, the forecasting period, which is going to be from 1990 all the way to, I think, end of 2023. Or beginning of 2023. So with that, and we have about 1,000 series for the leading bit because of the lags. So doing the principal component, you get only to 10 linear combinations. So it's a huge dimension reduction from 1,000 to 10. Okay, these are linear combinations of the data. Then we apply canonical correlation, get the cycles, and then the probability model using the probit regression. So what's missing here to you is how do we decide this is a recession, this is not a recession, okay? Okay, an important issue is, I mentioned this before, but let me reinforce, there is a huge lag on the NBR decisions to be known to the users, right? These are the delays here regarding, and we want to apply this in real time. So for us, the ideal thing would be to have the NBR decisions in every month, but of course, can get up to 21 months of delay, but that's solvable. How do we solve that? In the probit regression, the betas, which are going to be estimated, are going to be using only information up to 24 months ago. So in the forecasting sample, the biggest delay is 21 months. So we would be able to have all the zeros and ones to run every regression in the forecasting sample. So that's the only future information we have actually used, okay? But the cycles themselves, they are going to be period T cycles, because then we have the ragged edge problem solved, the principal component analysis implemented, then a canonical correlation with the cyclical parts, and throwing out noise and just keeping the C's current. So the betas are using lagged information, but the C's are contemporaneous, period T after the ragged edge problem solved, okay? Good. Rock curve. That's a rock curve. So thresholds. Probability is a number between 0 and 1. So suppose you want to use 0.5 at the threshold. Anything above that, you say, is a recession. Below that is not a recession. That's a threshold. What the rock curve does, but you don't have to use 0.5. You can use 0.7, you can use 0.3, you can use 0.1 or whatever. So if you vary the threshold, you can compute ex post the true positive rates and the false positive rates. And of course, as a forecaster, you want to go to 100% true positive and 0% false positive. That's the best you can do. So it's almost like an indifference curve, but the direction of preferences goes this way, the northeast direction, northwest, sorry. So first, let me show you results with the hindsight. So we run the several models and showing you the results, and then we're going to implement the real time, okay? With hindsight, that's a model that worked pretty well, okay? So we had the threshold use was 70%. 70%, I think, is this point here in the top. About 97% of true positive rate, so you're doing pretty well in terms of the model. But you only make mistakes about 4.4% of the time, so that's a pretty good model, okay? A bad model. Bad model, you see, you don't get very close to the perfect classifier part. And the reason is here. There we had only 50, here we have 50% of variance explained by the principal component bit, and here we have much less. So one thing I learned in forecasting very early is that parsimony is very relevant. It's fundamental. And parsimony is here, but not there. As you can see here, you have a lot of false positive rates. The recessions are in gray, and the pandemic is very thin, but it's here. Okay, and you can see that that's why the model it has a lot of false positive. Okay. Now, the real-time exercise. So we split the sample. We have data from 70 all the way to 2023. From 70 to 90, we just is the burning period, and we have a growing window after that. And we have a dynamic algorithm that starts with 40% coincident and leading explained variance with the principal component analysis. And then with that, we start the algorithm, let it run a bit, and start seeing which model. We run 9 models and let them, with different combinations of percentage of explained variance on the principal component bit. And then we let them compete. And we choose in every point T the best one, according to previous results, okay, in a growing window. And then we implement the best one at that point, okay? And how do we choose the best point? Well, we use the ROC curve. We can use the area under the curve, which is essentially the integral below that, the curve, the whole area. But we can focus also in like the top 10% bit here, or the top 20. Results don't really change a lot in the dynamic algorithm, whether you use area under the curve, the whole curve, or just focus on the top northwest bit. Doesn't matter. So results of the dynamic evaluation. So that's all. The only future information we used was that thing that, we know that you need at least 21 months with coefficients backwards. So here, the algorithm starts at 40-40. In 93, it changed to 50-30. And then from 96 on, 40-30, which was that best result we had with the hindsight. You can see that we're pretty much up there. And of course, you can choose if you want 100% false true positive, then you have to incur a little bit of false positive. But you can get a little bit less of false positive going left, okay? No, it doesn't really matter whether you use the whole area under the curve or the top 20 or the top 10, doesn't matter. The results change a little bit, the choices, but that's, as you can see, looking at this bit here, it almost doesn't change, okay? So, just to conclude, now let me show you a new project. This is doing the whole thing again, just using text. And then there is a lot you don't need to do, like the principal component. The principal component you need to do. The ragged edge thing you don't need to do because you have text every month. And that's the result of the text. So it's pretty much close to the data and is much more economical in terms of data. That's it. Thank you.
I'd like to invite Professor Richard to comment on the
All right. First off, let me thank the organizer for inviting me to discuss this very nice paper, and also for having my paper as well as part of the program. So I must say that I enjoyed very much reading this paper. So I will be focusing more on the econometrics part of the paper, which I believe is its main strength. So to be more precise, I really like how the authors use economic intuition to disentangle the business cycle signals from the noise in a large data set, hereby using a split between coincident and leading indicators. And I also like how they tackle the modeling issues arising from big data and also the real-time aspect of the forecasting experiment. Okay, so first, they use the expectation maximization algorithm to fill in the missing values in the data set, and especially to overcome the ragged edge problem at the end of the sample. And I think this is a clever idea because the EM algorithm effectively exploits the cross-covariances within each data set, right? And from there, dimensionality reduction is achieved via PCA to manage the large volume of data, right? And this gives us a bunch of factors connected to the coincidence and also to the leading data set. And yeah, these guys, they will only convey essential information to proceed with canonical correlation analysis. And yeah, so canonical correlation analysis will be the next step here. And I'm over here. And these will exploit the relationships between both groups of variables, so the coincident and the leading data set. And I think this is also a great idea because, as João said very nicely, we can obtain a linear combination for the coincident series that have maximum correlation with a linear combination of the leading series, right? And this means that we can extract from the business cycle only those portions that can be predicted by the leading indicators, right? So all the information that cannot be predicted by the leading indicators, they're just discarded. And the essential part here is what the authors called basic cycles or basis cycles. And these guys, from now on, will play a major role in order to construct the real-time prediction of economic downturns. So, well, the next step will be a first stage regression for each of these basis cycles. And yeah, so here these guys will be run against leading factors. But the ultimate goal is to get an estimate for each one of these guys here. So you can think about these VITs here as some kind of estimate for the leftover cycle variability that cannot be explained by the leading factors, right? Okay, and then all these guys will compose, they will be used as regressors in the structural probit model, along with the basis cycles. So you see that all the way through, the authors are very carefully thinking about how to extract the relevant information from the business cycle. And finally, the real-time prediction model will only be constructed using the contemporaneous business cycle signals that can be predicted with leading indicators. Okay, so another great contribution of the paper is the careful handling of potential data leakage from the future. This, of course, is not a problem on the right-hand side of the prediction model, but is mostly related to the NBR delays in dating recessions, right? And here the authors take a stance on how to overcome this problem, and they suggest estimating the parameters of the probit model using NBR information up to T minus 24 months. So these are the months that they lose when doing the estimation. So here I was wondering whether you could also use your recursive recession predictions as a proxy for these missing delayed NBR dates, right? Then you would obtain a full balance panel, and yeah, maybe this could lead to some lifts in forecasting performance, maybe not. Yeah, I guess it's worth the try. And from there, the authors also simply replicate the real-time deal with a 1 or 2 month forward shifts in the information set. And great news is that the results are very robust to this forward shift in the information set. And finally, once they compute these recession probabilities, model selection, and also performance evaluation is carried out by ROC curves, as João explained very well. And these are run against different thresholds, classification thresholds, and also across different model specifications that vary according to the principal components coming from the original data set. Okay, going on for the key empirical findings of the paper, the model yields high true positive rates, above 90%, and acceptable false negative rates between 5 and 8%. So yeah, this is great, but I would still like to see some comparison to well-established benchmarks in the literature. So I would like to see a statement of the kind, a big data setting has a value added of X% compared to this and that state-of-the-art model for economic downturns, right? And another suggestion that I have here is if you eyeball this very nice plot here, you see a lot of false positives in the first half of the forecasting sample. So why is that so? Is it because of the smaller number of observations in this region here when updating your forecasts? Or is it driven by the nature or some particularity of the economic cycles characterizing this first half of the sample? So yeah, maybe if you split your evaluation period into different subsamples characterized by different recessions here, this could shed some light into what's driving your main results, or even report some cumulative ROC statistics over time that could also do the job for you. Okay, and then next, the model selection indicates a very high risk of overfitting. So if you take a look at this very nice plot here, as from the 2000s, there is only a handful of coincident and leading factors that fully characterize the predictive content about business cycle dynamics, right? So yeah, there is a very high risk of overfitting, but the problem of using factor extraction is the lack of interpretability, right? So yeah, it would be nice, I was just wondering if you could also apply some other kinds of model like lasso or even Bayesian models with sparse priors, because they would combine the best of both worlds here. They would still reduce complexity in signal extraction, but keep the interpretability, which could be beneficial for policymakers, for example. Yeah, and finally, this is also a great result. Model accuracy is robust across different horizons and classification thresholds. But again, as I mentioned before, it would be nice to have some comparison to a well-established benchmark, right? And here are some final points like a robustness check with international data. So what you have here is the perfect data-rich environment, but what happens if you estimate the same model for a country with limited data? Would your results still hold? So is it dependent on the richness of the data sets that you have? And yeah, and finally, let me just provide one potential avenue for future research, which I think is very connected to your findings here. So one could exploit and extend your empirical contributions to a more theoretical aspect of economic forecasting. So answering what is the economic value of these reliable recession probabilities in a monetary policy theoretical framework. Okay, I'm going to stop here, but let me wrap up. This is a great paper. I recommend everyone to read it. And yeah, I would also like to see if you could transform your model framework into like an automated or practical early warning system for detecting economic downturns. This would be highly beneficial. Thanks.
So Richard.
So thank you for the comments. Let me go quickly over them. Whether or not we could shrink the 24 months that we used, that was an ad hoc decision, right? We knew that we had at most 21 months of delay for the forecasting sample, so we used that information. But as you saw also, the delay varies in different recessions. So we could get some gains on that for sure. And by reducing the delay for different points. But that's, again, using future information. So there's no escape from that, because you have to be able to have the left-hand side of the probit model at hand to run the regression. So there is no, and of course, you're not always going to have that in real time. Comparison to other models, this is, it was a tour de force just to put the paper together for the conference. So yes, we'll try to do that. If you have some suggestions of other papers, we'll definitely like to hear. Yeah, you're right that we have too many false positive rates. That's the most most of the problems with not just our case. There is this in the forecasting literature for recessions. There is this say, you know, I have a very good model. It forecasts 10 of the last 2 recessions. So that's exactly what we saw there. You know, just there's 2 recessions and the model was, you know, going off all the time. But that can be controlled by the rock bit, right? Because you can choose. You saw the threshold chosen was 70%, so that's pretty high. So that avoids the false positive. Although the graph shows the spikes, but decision is not exactly to choose that number. It's to say yes or no, and then use the confusion matrix to decide and compute the false and true. If we can use lasso, I think we can. I mean, there are other authors that I mentioned to you that before, the Serena Eng and Zhu Shanbai use. There is not exactly lasso, but they use a selection mechanism to get into the factors, which is very parsimonious. That can be done for sure. And robustness, yeah, I was happy that it didn't change much the results using different thresholds but although the thresholds don't change much, the true positive, the false positive, they change a bit too. So that's the key thing, is that use the proper ones. Thank you very much.
We have some time for a couple of questions from the audience.
João, first of all, congratulations on your paper. Very interesting, very nice paper. There's an older literature that uses the term structure of interest rates to forecast the recessions, and a more recent one that forecasts the whole distribution of the GDP. So I want to know if little comments from you, advantage and disadvantage from using your methodology and these other different methodologies. Thank you.
I was curious about the last chart you showed. I know it's not the paper, it's just a different paper with a similar objective. So when you say text, is it newspaper articles, earnings calls? What sort of text information you're using?
Okay. I was wondering if what you said at the end, that you forecast 10 of the last 2 recessions, right? That's a common result in the literature. And I was wondering if there is any value to this kind of forecasts. Do you actually, for instance, you quoted Hamilton, right, at the beginning? If you can't forecast, you can avoid them. So perhaps you're forecasting something that was avoided, for instance, or something that worried people at the time, and something happened. So perhaps by focusing only on actual recessions, you might be throwing away relevant information somehow. It's just a very speculative comment.
Okay, so I'm not sure I fully understood the question, but so Jim Hamilton said something what he said, why, if we can't predict recessions, agents are going to accommodate, going to respond, right? So consumers are going to consume less, and they adjust their budget. Firms are going to reduce inventory and things like this. So perhaps it's like you can think of like a smooth landing. Let's say we're in a central bank, so let's use smooth landing instead of a abrupt change. So I think that's what his idea was about. And I'm not a theoretician, so I'm not the best person to answer that, but it occurred to me that it could be the opposite. It could be just a self-fulfilling prophecy, right? So you forecast a recession, and people, oh, there's going to be a recession. There is an abrupt change of behavior, and then the recession happens immediately instead of along the line. So, but I'm not sure whether I'm answering your question. Term structure, that's a very good question. We know from it comes from a structural model that uses the stochastic discount factor, right? That the slope of the term structure, which is a difference between two maturities, a short and a long one, gives you predictability on the period in between, right? That's structural. And you can derive that analytically if you use like a known utility function. So you're right, there is predictability. And predictability comes into the leading part, right? So we can look at the curvature and of the, we actually use the data like that in the leading part, and it helps a lot. So you're right. But, so I think we're incorporating that for sure. But I know that there is a model of Fed, I'm not sure it's St. Louis or some other one, that looks only at that. That's kind of incomplete, I think. My view. I looked at their homepage, and this is kind of incomplete because they only use that, and they use future information to run the probability regression and get the probability. But then, if you want to do it in real time, you don't have the ones and zeros. So it's a problem, I think. And I deduced that from looking at their own page, and they have the zeros and ones as well, and there are parts that they couldn't have access to in real time. So it's an ex post thing, that's fine, but cannot be used in real time. And, texts, okay. So there is a database in the US of magazines and I think newspapers specialized, like Financial Times and Wall Street Journal. And these are available to use. I don't have access, but my co-authors do. They have access to that. So the key thing there is to transform words into numbers, right? And the very frequent words, that they don't mean anything, because like for or off or something like that, it's all the time that you observe. But the infrequent ones, they may give you some idea. And still, people use machine learning techniques and also principal component analysis later on that. So then they clean the database, and that's what we did, essentially. So it's several steps, but it uses essentially the words that come from this database. But I guess you can use AI and go a step further. Maybe that's what you're wondering about.
Without further ado, Professor Richard.
All right, I'm very pleased to be here with the opportunity to discuss the following topic: harnessing machine learning for real-time inflation forecasting. This is joint work with Aisha Meriane Schmidt and Guilherme Vale Moura. Okay, recent events have shown that inflationary waves can unfold extremely fast all over the globe, bringing to light an urgent need for accurate projections of current price developments that could come in handy for a more timely reaction of monetary policy. Nevertheless, tracking inflation dynamics in real time is quite challenging and falls short given that official price statistics are only published with a certain time delay after the fact. So just waiting for official releases might not be the most efficient course of action for central banks and practitioners who constantly need real-time assessments of the economy. Fortunately, we can make use of timely signals coming from high frequency and quickly released data to better anticipate swift inflationary shocks, right? And this is a technique called nowcasting, which is like forecasting, but focus on the current month while official numbers are still in the making. Okay, so it's like trying to read a book while still writing it. So the ultimate goal here is to harness the power of machine learning methods for real-time inflation nowcasting, and our work has some key practical implications, going from timely and more accurate economic insights for policy formulation and asset allocation to better jumping off points for short and medium-term inflation forecasts. All right, given this background, the recent decades of persistently high inflation experienced by the Brazilian economy suits perfectly as the case study to tackle our research question. More precisely, the official CPI rate, here illustrated by the black line, displays multiple episodes of rising inflation that easily reach the double-digit mark, mainly caused by domestic turmoils or global shocks like the pandemic. So it's like following a Marvel movie series where the villain always comes back there for a while, and calm periods are those characterized by a 4 or 5% inflation rate, right? Moreover, Brazil has a variety of broad non-official price indicators that are released by different agencies, and they essentially differ in terms of the sampling period and the targeted prices. And they are here illustrated by all these colored lines. And as you can tell, they highly correlate with official CPI dynamics and thereby provide leading information, even though they target different veins of the population or even different sectors of the economy. And as you may know from the previous presentations, the Brazilian Central Bank surveys market participants on a daily basis about their inflation expectations, which for us could serve both as a powerful explanatory variable and the ideal benchmark, right? So despite all the problems behind the updating of these forecasts, as João mentioned, we believe these are strongly credible because the central bank also publishes a top 5 ranking of them. So yeah, there is some incentive for them to be performing well in this survey, right? So all in all, Brazil provides a unique economic environment marked by frequent inflationary episodes that are well suited for a nowcasting exercise. Okay, our contributions are threefold. First, we construct a real-time database consolidating key macro-financial indicators for the Brazilian economy, and these were previously dispersed across the internet and partly stored by Bloomberg. Secondly, we are among the first attempts to implement a broad range of machine learning methods into a nowcasting model for inflation. So here we apply a mixed frequency architecture, which allows machine learning to thrive because we facilitate model information by separating all the real-time information flow from each predictor in the data set, right? So this means that we allow for the effective use of both linear and non-linear machine learning methods, hereby assessed via shrinkage and non-linear tree-based methods due to their good forecasting and interpretability capabilities. And third, we learn key lessons from a practical standpoint. First, we find that hard price data conveys valuable predictive information about inflation dynamics and that are beyond what is contained in the survey of professional expectations. And we also find that targeted variable selection performed via shrinkage, especially the lasso, outperforms nonlinear tree-based methods. And it's highly beneficial. It leads to huge nowcasting gains, especially during the pandemic, where professional forecasters had a tendency to underestimate the rapidly evolving inflationary environment. And last, we also report that the model specification must be free of ragged edges and guided by the real-time flow of price data in order to achieve better results. Okay, here is a summary of all macro financial indicators that are well suited for nowcasting the official CPI rate targeted by the Brazilian Central Bank, here denominated as IPCA. And this guy is usually reported in the second week following the end of a reporting month, right? In a nutshell, we can use timely signals coming from two groups of price indicators. The first group is the group of monthly price indicators, which covers mostly the first half of the reporting month and are usually released in the third or fourth weeks of the reporting month. For example, the IPCA 15 is a mid-month version of the official one, which gathers data from the 16th of the previous month up to the 15th of the current month, right? So you see there is some leading information via the IPCA 15, and the same, all the remaining indicators here are similar in spirit, but they just differ in terms of the sampling period and also in terms of the targeted prices. Moving on, we also use weekly price indicators published with 1 or 2 days lag only. Here the IPCS and the FIPE, they try to closely mimic the behavior of the official target at a higher frequency, but each one accounting for different income levels of the population in the basket. And the third group comprises daily information from financial markets that are potentially correlated with inflation expectations, like short and long-term interest rates, commodity and stock price indices, and also exchange rates, right? And finally, we have the daily series of experts' forecasts from the survey conducted by the Brazilian Central Bank, and more precisely, we use the median across more or less 100 active participants in the survey. So you see there, all of these indicators, they form a highly populated timeline of data releases throughout the reporting month, which is what we need for a real-time nowcasting exercise. Okay, moving on to the framework, we employ an unrestricted mixed frequency architecture in order to integrate high frequency observations into a monthly model for inflation, which has the following key ingredients. On the left-hand side, the inflation target measured in month-on-month rates. On the right-hand side, we have the prediction function specific to horizon age, connecting to the predictor set containing an autoregressive term, monthly seasonal dummies, monthly predictors, monthly price predictors, and most importantly, high-frequency predictors and their legs. And these guys here, they will be sampled W times more frequently than the target, right? So here we need to take a stance on how to incorporate high-frequency information. What we do is we set 4 days in which we update our nowcast within the reporting month, more precisely on days 8, 15, 22, and end of month. And this allows us to apply a monthly to weekly combination where we transform all high-frequency data into weekly time series containing the latest month-on-month rates by the time of these defined dates. Okay, and one last comment here. We also allow each one of these guys to have its own coefficient so that we can fully exploit the power of machine learning methods. Yeah, of course, this leads to over-parameterization, especially in a macro context with relatively small sample sizes. But yeah, we can still we can overcome this problem by using machine learning methods and effectively use both groups, linear and nonlinear methods. Okay, the machine learning methods that we use, they have been enjoying growing popularity in economics literature, and they are here divided into shrinkage or tree-based methods. So the key idea of shrinkage methods is to select the relevant predictors within a large data set. And this is done via penalized regression schemes. So specifically, we use the hybrid elastic net estimator, which solves the following penalized least squares problem, where lambda here controls for the amount of shrinkage, and alpha oscillates between lasso and ridge regression. And both of these parameters, they will be estimated in a data-driven way using time series cross validation, right? The only problem with these estimators is that they might struggle with multicollinearity, especially in price data. But we have found that in our application, these estimators, they efficiently capture the strongest high-frequency signal at each nowcasting day. And we also apply the recently proposed and promising sparse group lasso, MIDAS, which simply imposes a group structure into the penalty term, right? And the group here is defined as all high-frequency legs of a single predictor. Okay, on the other hand, we also apply nonlinear tree-based methods, and these are non-parametric approaches, meaning that we don't impose any restriction whatsoever on that prediction function that connects the predictor set to the target variable. So the idea here is to, using this illustration, is to find optimal cutoff points that divide the data set into smaller regions. And these will assign different predictions to the target. So here, SPF being smaller than 1.2 defines our first split of the data. If this condition is not satisfied, then the prediction for the final target is 1.34. If it is satisfied, then we continue to the next leaf node here, and so on and so forth, following this kind of a recursive binary split scheme, right? The only problem with individual trees is that they are prone to overfitting issues, but here we only work with the class of random forest algorithms and some variants of it, which control for overfitting by averaging across several non-correlated trees. And yeah, and we also include the Bayesian counterpart to the random forest called BART, and these guys estimate sequential trees using the estimated residuals from the preceding tree. Okay, so it kind of captures some leftover variability. Okay, here are the first results of our real-time nowcasting exercise, whereas we apply an expanding window scheme with data from June 2004 up to December 2022, whereas the evaluation period starts in 2013. So this table here shows the relative RMSCs of each one of our machine learning methods compared to the median of experts' forecasts across these different horizons that we consider. So values smaller than 1 indicate outperformance compared to the experts' forecast, right? So our results here, they highlight the effectiveness of shrinkage models compared to nonlinear tree-based methods, right? So this means that targeted variable selection performed via shrinkage leads to exceptional nowcasting gains. And yeah, I will show you that this is particularly true during the pandemic. But here I would like to highlight that these gains are even higher at longer nowcast horizons. So for example, on days 8, 15, and 22, we are able to see predictive gains of 17, 13.5, and 17% compared to the benchmark. And these gains, over 11%, they even hold if you compare to the top 5 forecasting institutions in the survey, right? So what is driving the poor forecasting results of our nonlinear tree-based methods? Well, even though they can capture and uncover all these complex nonlinearities within inflation data, they might require huge amounts of data in order to perform well, right? And we believe that in macro scenarios, these methods are still ill-equipped to lead to good forecasting results, right? And we actually show that a lasso pre-selection step increases by a significant margin the performance of a particular type of tree here. And we also believe that given the minor presence of nonlinearities in short-term inflation dynamics, then linear methods just provide a better balance between approximation and parsimony, right? Okay, now the question is whether relative performance is constant throughout the evaluation period or largely driven by inflationary shocks. So this is the role of the following cumulative sum of loss differentials, here reported for our best performing model against SPF expectations. So in a nutshell, values above the 0 line here, they indicate that we are doing better compared to expert forecast, right? And this is particularly true for most horizons, even though relative performance here is kind of constant and boring until the pandemic hits the globe over here. But then a lot of action begins, right? Namely, the inflation surge that we observe over here in this period is a game changer in terms of loss differentials, because professional forecasters had a tendency to underestimate this movement, while our machine learning method better adapts to this swift change in economic conditions, leading to all these major nowcasting gains, right? And I would also like to draw some attention here to the importance of timely updates across different information sets, because you see that the nowcasting gains are much higher at longer horizons on day 8, 15, and 22, if compared to only moderate gains that we have at the end of the month, right? Okay, and variable selection performed via lasso also facilitates model interpretation, as shown here by the group relevance of each predictor. So this is kind of, and this is divided across different subsamples in evaluation. And so this is like asking who did more work on a group project. And here what we see is that survey-based expectations and weekly price indicators, they deliver a more sparse model structure at longer nowcast horizons on days 8 and 15, here, and also in the last panel. And so our model-based nowcast, they suffer more influence from SPF and from the weekly price indicators. So these are the good anchors for good performance of machine learning methods. And yeah, this is particularly true for the pandemic period where hard price data and some informed judgment in SPF data, they become even more influential for our nowcasts. On the other hand, daily financial variables, they only play a minor role because they don't provide much informativeness about current inflation dynamics. And at shorter nowcast horizons, at the end of the month here, for example, the model structure becomes more dense, which coincides with more data releases becoming available from these monthly price indicators throughout the reporting month. Okay, then let me wrap up the presentation by emphasizing once again the potential of the Brazilian data set for inflation research, because there is a lot of action going on here in recent decades besides COVID-19, as well as high-frequency signals and timely signals that are not available everywhere, like the daily survey of professional forecasters, and also all those different price indicators, which combined with shrinkage methods can actually improve upon survey-based expectations. So yeah, this is kind of bringing more spice to this literature. And looking ahead, one could further investigate why, via simulation methods, why the nonlinear tree-based methods are not performing well, and how could one improve them, right? Yeah, so let me stop here. Thank you very much.
Okay. Yeah, so I want to thank again the organizers for allowing me to discuss this very interesting paper and also to present my own work. So I know I'm the last thing you will hear from until the day is going to end, so let me be brief, hopefully. So this, well, as Richard just show us, it's a very complex and a very timely paper about how you can do nowcasting with machine learning techniques. So basically the paper is going to combine tools with a mixed data sampling with the MIDAS approach, typically they use to nowcast inflation in this case. The aim of the paper is to evaluate different methods to produce a nowcast, which the authors group between linear shrinkage and nonlinear tree-based models. Among the linear shrinkers, as Richard just told us, you got the elastic net, lasso, rich, and a sparse group lasso. All of those framed within this MIDAS structure. And among the nonlinear tree-based methods, you got the random forest, the local linear forest, and the Bayesian additive regression trees. The evidence tends to favor shrinkage methods. And is, as you just saw, is robust for different horizons, particularly when you cut the month in weeks. You can see that obviously the method is always trying to support all the shrinkage methods with respect to this nonlinear tree estimator base. And finally, it's important to mention that it seems key to incorporate the predictions from professionals according to the results, and also you have to feed all these models using this real-time data releases that you observe, as Richard was telling us, literally every day within a month. Okay, so I must say that I'm not much of an expert in this material, so I learned really a lot by reading it. I think it tackles a very interesting and very hot topic in the literature, which has an exponential interest for both the policymakers and academics. And in terms of how I'm going to discuss this paper, I would prefer to, rather than discussing the machine learning techniques, I'm going to focus my discussion on a few suggestions that I think can make the paper more appealing for, like, let's say, a broader audience, besides the specific techniques. So the first comment that came to my mind when I was reading this is that why do we need a nowcast? What's the relevance of a nowcast? So it's a fact that apparently according to the paper, the machine learning methods can improve nowcasts for the monthly inflation. But why do we need the nowcast? Actually, I quote this from the paper. So the authors argue that, well, short and medium-term inflation forecasts highly benefit from taking high-quality nowcasts as jumping-off point. I think this is relevant. I think this is key. So this is why, at the very end, we need the nowcast, because through the nowcast, we want to inform long-term forecast. And I would like to see an exercise where you see, well, how much precise will be like a long-term forecast. Think about 1 year ahead or 2 years ahead. If you are using your machine learning nowcast monthly inflation compared to just taking the last piece of evidence that you have and just project that. I think this will be a very nice quantitative point of why this type of exercises are relevant. At the very end, I think we just need better ways to predict long-term inflation, and if this is a useful tool, and I want to see how that can be done. Second comment, so you didn't really mention it, but among the list of variables that you use for the nowcast is this APC 15 variable. This is a very, very powerful indicator that I don't know if this is common in other countries. I know in Brazil you have it. Because at some point you claim that one of the contributions is to extend this beyond what is being the typical focus, which is either the US or Europe. So my question would be, how common is this like inflation preview statistics in other economies? Or to which extent this variable is actually driving the result? I was thinking about like in a football analogy, if I may. If you need to predict the outcome of a match, if you're allowed to see the first half of the match, at least I would say that in expectation you will be more accurate predicting the final result of the match rather than trying to predict the result at the very beginning. So it's a very, very powerful thing. So I would like to see some exercises when you actually remove this and see how better or worse this machine learning techniques become. Especially because, you didn't mention it, but it's in the paper also, the weight to the APC 15 variable becomes really relevant towards the end of the month, which is obvious, which is when the variable appears. And the SPF expectations kind of lose importance. I think this is really because, well, professional forecasters are really tilting their survey response towards the APC 15, and that's why you get really, by construction, this is a conjecture at this point, they're tilting their predictions toward this variable. So if we remove this variable, it's still true that the SPF expectations become less important towards the end of the month. That would be my second big comment. And the third thing, again, looking through the lens of an ignorant in machine learning methods as myself, I didn't quite get why, at least intuitively, why the lasso and wrist and the elastic net performed so much better during the pandemic. So you show us this figure at the very end. So the gains are massive, and I would like to see more like a discussion why this is the case. Is it different because perhaps the benchmark is also changing? Perhaps the SPF benchmark, the professionals are doing much worse. So is it because the machine learning is better, or is the professionals doing worse? You see that we have lots of evidence that, well, during uncertain times, forecasters revise more, they make more systematic errors, and they do bigger adjustments. To which extent this is driven by forecasters becoming worse relative to the machine learning techniques becoming better, you see? And then, as a final comment, I would say that, well, you do have this like menu of machine learning techniques. I was wondering if you can combine all that weighting somehow to get like an ex post weighted average of all the techniques, how better that would be just to look at each of the techniques independently. I was thinking about doing like a very simple weighting them through their ex post forecast error, for instance. How much accurate you can become if you weight everything, you put everything inside. And also, there's a recent paper about how to use actually machine learning methods to combine forecasts. This is the reference if you want it. Because perhaps there's a gain, not look at everything independently, but again, if you combine everything together. But besides that, very interesting, and I really, really learned a lot about this. So, thanks.
Yeah, many thanks for all these useful comments and suggestions. Yeah, I really appreciate the effort that you put into reading the paper and compiling all these nice recommendations. Yeah, so the thing with the jumping off point, this I guess this will be another paper. So I think it's not worth to extend this one here to include this analysis. I guess it's worth a separate paper. Many thanks for reminding that. Yeah, so this is something that we have already discussed in the beginning of the project, and we would like to see what's the impact of improved nowcast into long-term inflation forecasts. Okay, and then the story with the IPCA 15. Yes, you're right that the release of the IPCA 15 is driving most of the results. However, SPF expectations, they also include this information. So yeah, vis-a-vis, I guess there are some gains from using machine learning. And yeah, so this is what sets us apart from the predominant focus of the literature on US or Euro area inflation. I guess there is a lot to learn about inflation nowcasting with Brazilian data. And yeah, I'm totally on board that we need to do this exercise of removing the IPCA 15, see what happens. We have done this with the SPF expectations, and the results were not that satisfying. Actually, we need that informative data in order to get high accuracy. But yeah, we're going to do this exercise, see what happens if we remove the IPCA 15. And yeah, the forecast combination with exposed errors, combining all the machine learning methods that we implement here is a great idea. Yes, I haven't thought about that before, and yeah, many thanks for that. I'm gonna read that literature tomorrow and yeah, see what we can do with it. Yeah, many thanks.
Well, still have time for a question from the audience. Yes, I would like to thank everybody for presenting the paper. I'd like to thank the audience and ask kindly for them to wait. We're going to have now Deputy Governor Diogo presiding the award ceremony, and after that we're going to have some cocktail.